Hello, my name is Yohan Beugin. I'm a PhD student in the Sys lab at Penn State, where I'm advised by Professor Patrick McDaniel. Today, I will be presenting how to build a privacy-preserving smart camera system, a work that was done with my colleagues acknowledged here below. First, let's see what is a smart camera system. Smart camera systems are used by people to remotely monitor their home while they are away, for instance. These systems are very convenient and also very popular, as we can see here on the right on this map of the United States, where each point represents a location of some of the devices sold by Ring, an Amazon company. However, their use is not without loss. And over the past few years, we have seen different reports about issues and privacy concerns about this system. Here are a few examples I would like you to focus on. This example questions the amount of trust that users need to place into device and cloud provider. For instance, users might be worried by the fact that their device provider is partnering with law enforcement to facilitate video sharing, or that employees of some companies are abusing their access to see users' videos. What all these examples demonstrate is the fact that users do not have control over their data and over their system. So, we would like to build a privacy-preserving smart camera system. Here is a threat model in which we are going to operate for that. We are only going to consider the smart camera and the device controlled by the owner to be trusted. Anyone else and any other third party is considered as untrusted in our design. To build such a privacy-preserving smart camera system, we need to return control to users. And at the same time, we still want to support commercial features that are the main reason why these systems are so popular. It's going to be this balance between security and privacy on one hand and like usability on the other hand that is hard to achieve. For instance, if we want to return control to users, we would like to use end-to-end encryption in our system. If we do so, we are effectively returning control to users as owners are the only one able to access the videos. However, using end-to-end encryption introduces new questions and challenges, such as how do we establish root of trust between devices in such a setting where we can only trust the owner and no one else? And also, how do we manage all those encryption keys, especially to support commercial features such as delegation? So now we are going to focus on those two main issues. First, how can we establish root of trust between devices that are unknown to each other? To do so, we would like to establish a secure communication channel between those devices so that they can further on negotiate encryption keys or secrets for the life cycle of the rest of the system. We would like to use authenticated diffie-hellman key exchange to do so. We are going to do it the following way. The smartphone and the smart camera system are going to pair through Bluetooth or Wi-Fi. And then we are additionally going to use an out-of-band physical channel to verify that each device is actually speaking and communicating to the right device. This is to mitigate any man-in-the-middle attack. In our proof of concept, we use a physical channel, which is a visual channel, by using QR codes that we flash and in which we embed some details. So this is how we establish this secure communication channel from where we can start building the rest of the root of trust for the rest of the system. Now, let's see how in our end-to-end encryption system we can manage all these encryption keys. For that, we are going to use a binary key tree that is built the following way. From a seed key, we are going to be able to derive lower keys in the tree by applying a hash-based key derivation function, or HKDF. This HKDF function is a one-way function. This means that we can only derive lower keys from upper keys and not the other way around in this key tree. This is going to be an important aspect for the rest of the system and for its privacy guarantees. So in our system, recall that after initialization and pairing, we have the smart camera and the smartphone connected through a secure communication channel. Through this channel, they are going to negotiate a seed key that is going to be the root of this key tree. Then this system can go on their own way to derive the lower keys as they know the HKDF function. At the very bottom of this key tree that we are able to derive are like the keys that are going to be used to encrypt video frames that are in the same epoch. An epoch in our system is just a fixed time window or interval, and in our proof of concept, this length is of 10 seconds. So this means that every 10 seconds the keys are rotated. And so thanks to our key tree structure, we are able to efficiently manage the keys and store them as we can derive them from upper keys. And we are also able to support key rotation. Additionally, this key tree structure is very convenient to support another popular commercial feature, which is delegation. And in our system, we are able to do a very fine-grained delegation. Let's say, for instance, that the owner would like to share some videos with some shared users. To do so, they only need to figure out which portion of the key tree they need to share with the delegatee. As illustrated here on the slide, if the owner wanted to share the red portion or like the blue dotted portion of their video, they would need to share only the corresponding key and no other key. And then the shared user would be from those keys be able to like derive lower keys and access the corresponding encrypted videos and no other videos that the owner didn't share with them. Alright, so in our paper we introduced a proof of concept of a privacy preserving smart camera system that we call Cactus. Here is Cactus at play while live streaming videos. Our system doesn't support only initialization, live streaming, or delegation, but also other commercial popular features such as video deletion, access recovery, and factory reset. For sake of time, for this presentation, I'm going to defer the details of the rest of this protocol to the paper. And I'm going to speak now about how we evaluated our system. The evaluation of Cactus was threefold. First, we carried out a security analysis to prove the privacy guarantees of our design. Cactus enforces the following three rights for owners. First, the right to not be seen by leveraging end-to-end encryption. Then, the right of sole ownership, as owners in our system are the only one who knows the encryption keys. So they are the only one able to mediate access to them and to the corresponding videos. Finally, owners have the right to be forgotten. This means that owners can delete their videos, or more specifically, they can delete the encryption keys, rendering recovery to them impossible, even in case of coercion. Then we perform a performance evaluation of our system to figure out how it behaved. Here in this table, we present the average time delay of each operation that is carried out by the camera or the smartphone application while we are live streaming. As you can see, the performance of our system are reasonable as our latency is about 1 second. Something to notice is that the main contribution to this delay and to this latency come from networking operations such as uploading and downloading the encrypted frame to or from the cloud storage, which is a point that is worth noting that we haven't optimized at all in our proof of concept. So further improvement and better performance is expected here. Alright, so finally, if building a privacy preserving smart camera system is great, it is even better if it's usable. Thus, we perform a functional user evaluation with 10 participants to try to identify the potential issues in our design and in our protocols. Here are the main takeaways. The participants found that our system was usable and that our application, our smartphone application, was simple to use and to follow the instruction. They all were impressed by the fine granularity at which they were able, with Cactus, to delegate access to someone else to their videos. And they also thought that the quality of the videos in our of the live streaming was sufficient for purposes of a security smart camera system. They noted two potential improvements if Cactus were to deploy as a commercial system. The latency should probably be optimized further, as discussed earlier, and that they also would like to see the recording and the live streaming triggered in Cactus with some motion detection system. These are two engineering problems that can be solved applying networking optimization on top of our protocols, or just adding additional sensor or piece of software to the smart camera device to support motion detection. So, as a conclusion, to design a privacy-preserving smart camera system without relying on anyone except the owner, it is important to establish a root of trust that needs to be maintained across the full life cycle of the system. In Cactus, we have used for that different encryption and pairing techniques to encrypt and isolate access to the data, and also support different features such as fine granularity, delegation, deletion, and access recovery. Finally, it is worth noting that our protocols are not only restricted to smart camera system, but are also readily applicable to other IoT devices, recorded time series data. More details about the protocols are available in the paper, and the implementation of our proof of concept can be found at the following link.